Okay, so what we want to do now is an example of using this theorem about Lagrange multipliers. So let's recall the theorem. We have a function, a C1 function, which we call the target function. And we know that it has an extremum at a specific point, x0, y0. And that extremum is only among those points satisfying a certain what we called constraint. The constraint is given by some other function g, which equals to 0. So this is some relation of points between x's and y's that restricts the points that we're looking at, seeking the extrema for f. We're assuming that g is also a C1 function and that the gradient of g is non-zero. Then there exists constant, real number lambda, such that the gradient of f plus lambda g at that point is 0. Okay? And the way to use this theorem, which we're going to show in an example in just a minute, is if we're looking for points that are critical, that are potentially extremal, what we do is we find points that satisfy this. And this breaks into two separate equations. The derivative of f plus lambda g with respect to x has to be 0. The derivative of f plus lambda g with respect to y has to be 0. Plus a third equation, which is g has to be 0. Okay? So let's do an example. So here's the example. Here's the example. Find the minima and the maxima of the function fxy equals x squared plus y squared minus xy minus x minus y in the domain D, which is the set of all points x, y in the plane, satisfying that x plus y is less than or equal to 3, and x is greater than or equal to 0, and y is greater than or equal to 0. So what do we have here? Let's draw D first. D is rather easy to draw in this case. So here's a bird's eye view of the plane, of the xy plane, where the function is defined. And x greater than 0, y greater than 0 simply means that we live in this first quadrant, right? And x plus y is less than or equal to 3. That means y is less than or equal to, let's rewrite that. This is the same as writing y is less than or equal to minus x plus 3. So y equals minus x plus 3 is a line with slope -1 crossing at 3. So it's this line. This is y equals minus x plus 3. Right? And saying that y is less than that means that we're in this triangle. This is the domain D. Does everybody agree? Good? Okay. Now, where is the function? Where's f in this picture? Exactly, above it, but above it means here, right? Because in this drawing, this is a bird's eye view of the domain. So the graph is somewhere here. Does everybody agree? Does everybody understand why I'm doing this? Okay, so the graph of f is somewhere here. F is defined in the entire plane, right? There's no restriction. It's a polynomial function. But we're only seeking its minima and maxima on this domain. Okay? How do we approach this? Well, we break it into two phases, two steps. Step 1, we use Fermat's theorem to find local minima and maxima inside the triangle. Points where the gradient of f vanishes, where both the partial derivatives are 0. We'll find points satisfying that only in this domain. We may, when we do it, maybe we'll find a point here and a point here, but they're not relevant. to our problem. Okay? Then we're going to have to look at the boundary of this triangle, which is made up of 3 separate segments, okay, and find points on which perhaps f attains greater values or lesser values. Okay, so we're then going to look for constrained minima and maxima of f only along these 3 lines, and those are not necessarily going to be points where the gradient of f vanishes. Right? If the graph of f looks something like this, or let's now assume that the xy plane is on the floor. If f looks like this, if this is the graph, and we're looking at, if we're looking at this line, maybe the minimum is here, right? And the gradient is not 0. Okay, clear? Okay, so step one, find critical points inside D. Inside, I mean in the interior of D, not on the boundary. Okay? And how do we do that? How do we do this? We take the partials of f with respect to x and y and set them equal to 0, just like we did previously. Okay? So what's the derivative of f with respect to x? It's 2x minus y minus 1. Do you agree? And we want this to be 0. Simultaneously, we want the derivative of f with respect to y to be 0, which is 2y minus x minus 1. So we want this to be 0 as well. So points satisfying these 2 equations, points xy satisfying these 2 equations, are local critical points if they happen to be inside this triangle D. So this triangle, this point is 3, this is 3, and this is 0. If they happen to be inside this triangle, then we're going to consider them as potential global minima or maxima for f on this domain. Okay? So let's solve this. We want to solve this system of 2 equations. It's a very trivial system of 2 linear equations and 2 variables. You can do it in whatever way you want, right? If you really want to, you can set up a coefficient matrix and do it like you do in algebra, but that would be not very efficient, right? But if you want to, you can practice. Let's do what? Let's write from this one, let's write y equals 2x minus 1, plug it into here, find x, and then find y back. So y equals 2x minus 1, that's from the first equation. We're going to plug it into the second equation, so we get 2 times 2x minus 1 minus x minus 1 equals 0. Therefore, what do we get here? 4x minus x, 3x, minus 2 minus 1 minus 3 equals 0. So 3x equals 3, so x equals to 1. Do you agree? And now we want to plug that back to find y. Y was isolated here, so x is 1, 2 minus 1, so y is 1 as well. So the only critical point, the only local critical point we found for f is the point 1, 1. Let's check if this point, so 1, 1, this point is a critical, a local critical point of f. And are we interested in this point? We have to check if it lies inside D. If we care about it at all, let's look back at D for a second. The point 1, 1 is somewhere here, so it's a legitimate candidate, right? Look here, please. Hello, this board. Thank you. So the point 1, 1, which lies here, this is the point we found, is a potential candidate for being a minima or a maxima of f on D, right? So we remember that point, and we move on to finding other points, and other points, that's going to be step 2, are points along these 3 separate boundary lines. Okay, so let's do that. Step 2. So maybe let's write is a local critical point of f inside D. We just verified that it's indeed inside D, therefore we're interested in it. It doesn't mean yet that it's indeed a minima or a maxima. We have to classify it, we have to compare it to other values. We'll do that at the end. So step 2 breaks into several partial steps. Okay, why? Because remember that the boundary of D, okay, so let's write first, find extrema or critical points on the boundary of D. Okay, the boundary of D is comprised of 3 separate segments. It's a triangle, right? So we have to treat each segment separately. Moreover, there are those 3 corners. Let's look once again at this picture of D here. We're going to have to look separately at each of these 3 segments. Each one is a different constraint. Each one is going to be different, given by a different gxy equals 0, right? Here it's simply y equals 0. Here it's simply x equals 0. And here it's x plus y minus 3 equals 0, right? Furthermore, we're going to have to separately check these 3 points, these corners of the triangle. And why is that? Because when we're looking for, what are we finding when we're looking for extremal points on this line? We're looking for local minima and maxima that satisfy this constraint, and we're doing it in terms of a Fermat-like theorem. We're looking for derivatives that vanish, right? But that again could happen at endpoints of the interval. And here at the endpoint, if we would try to consider the entire triangle as a constraint, then the endpoints would be points at which that constraint is not C1. It's a cusp. Do you agree? Okay? So any way we look at it, we have to check these 3 points separately, just like when we take an interval and a single variable function, we check the endpoint separately. Do you agree? Okay? So we have to check 3 separate constraints plus 3 separate points. Okay? Let's do that. So first of all, let's do, let's call it 2a. 2a is going to be on x plus y minus 3 equals 0. That's on the hypotenuse of that triangle. Okay? So what do we get on that hypotenuse of that triangle? Let's do it, we will use Lagrange, the method of Lagrange multipliers. Okay? So how do we do it? We have to set up a system of equations. What are the equations going to be? There are going to be 3 of them. The first one is going to be the derivative with respect to x of f plus lambda g. Okay? So let's write it first in general and then do it for the concrete example. So fx plus lambda plus lambda gx has to be 0. Fy plus lambda gy has to be 0. And g itself has to be 0. That means the point lives on the constraint. Do you agree? This is the system that we have to write. Let's do it for our example. So the derivative of f with respect to x we already calculated. It was 2x minus y minus 1 plus lambda. The derivative of g with respect to x, let's write g down here, because then we'll see it. So g was x plus y minus 3, and equals 0 is this. What's the derivative of g with respect to x? It's just 1, so it's just plus lambda times 1. So this has to be equal to 0. The derivative of f with respect to y we calculated previously was 2y minus x minus 1 plus lambda times the derivative of g with respect to y, which is 1 again. So this is the system of equations that we have to solve. Do you agree? Points satisfying this are points on this constraint, on the hypotenuse, which is part of the boundary of the domain D, that satisfied the theorem on Lagrange multipliers, which says that these expressions, the gradient of f plus lambda g, is 0. Clear? Do you see 3 variables, 3 equations? X, y, and lambda, 3 equations. Solving it, you can do in whatever way you like again. You could find lambda, but that's the only thing we don't care about. We only want x and y that satisfy these 3 equations. Okay? Sometimes en route we'll find lambda as well, and sometimes not. Clear? So let's solve this. I'm going to do it the following way. It's always a good idea, I've said it before in various situations, take a step back. I'm next to the board, I'm taking a step back. Now I'm further away from the board. Take a step back, look at the system, see if there are some basic algebraic manipulations that you can do to have the solution pop up at you without working at it, like straightforward. Take one, plug it into the other, and sometimes the straightforward way turns out to be just longer. Okay, so in this case, I'm going to write the first two equations as 2x minus y equals 1 minus lambda, and 2y minus x equals 1 minus lambda, by moving these to the right-hand side. And I'm going to leave this one as is for a minute. And now I'm going to, subtract or add? Subtract this one from this one. Okay, so from these two, I get 2x minus x, so 3x, minus y minus 2y minus 3y equals 0. I subtracted the 2 equations. Therefore, 3x equals 3y, therefore, x equals y. Do you agree? Okay. And now I'm going to plug that into here. So x equals y. So now from this one I get x equals y. So 2x minus 3 equals 0. Therefore, 2x equals 3. So x equals 3 over 2. And x equals y. So both x and y equal 3 over 2. Clear? And note that in this case, I did not find lambda along the way, and I don't care what lambda is. I can find it now. I can plug in x equals 3 over 2, y equals 3 over 2, and find lambda, but I don't care. Lambda is kind of an auxiliary variable here, and I don't really need to know what the value of lambda is. Yes?
Is it just a coincidence that in step 2 you found that, in step 2a you found that x equals to y, and in step 1 we found 1, 1?
It is a coincidence. There's going to be step 2b, 2c, 2,3, and we're going to find other points which don't satisfy x equals y. It really is a coincidence. I mean, I've never thought of it, but maybe because of the symmetric nature of this function in x's and y's, it happened in these points, but it could be. It could be. F is symmetric in the roles of x and y. Okay. Okay, so now we have another point to consider. So we found the point 3 over 2, 3 over 2. Maybe let's put some, we're going to need to erase some boards as we go along, so let's keep these in boxes so we remember to consider them. So we had this point here, and we had on this board, we had the point 1, 1. So we have 2 points so far. Now we need to go to continue step 2. It's going to be called 2b, and we're going to look at the line x equals 0. Let's do it here, okay? 2b, because it's considerably easier. On x equals 0, that's the the side, the y-axis, the side of the triangle, we could use again the method of Lagrange multipliers, but that would be working too hard. Because what does it mean x equals 0? We're looking at fxy where x is 0. Okay, so let's define f of y to be little f of points of the form 0, y, because x is 0, right? So what do we get? The function was x squared, that's 0, y squared, minus xy, but x is 0, minus x, but x is 0, minus y. This is the function. It's a function of one variable, and we need to find its minima and maxima. Do you agree? Okay, this is precisely like what we did before we discussed the method of Lagrange multipliers. Plug in the constraint into the function, it becomes a function of a single variable, and find its minima and maxima, just good old Calc 1 way. Good? Okay, so in this case, f prime of y, capital F, the function defined at x equals 0, is 2y minus 1. We want to set that equal to 0, so we get 2y equals 1, y equals 1/2. What is x? 0. So we get the point 0, 1/2. That's the candidate along the part of the boundary, which is that the y-axis. Clear? And similarly, I'm not going to write it because it's completely analogous to C. On y equals 0, we're going to get the point 1/2, 0. Clear? And now we have to throw into the pool of candidates the 3 corners, okay? Because we're not going to be able to pick them up like this, for example, right? The point, for example, 3, 0, or 0, 3, the point 0, 3, is not a critical point of this function, but it's an endpoint of the segment on which we're checking this function. So it is critical. Clear? Good. Okay, so we're going to add, so let's call it 2D. Let's do it. Let's do it here. 2D. Consider also the 3 endpoints, 0, 0, 0, 3, and 3, 0. In general, that's in this example, in general, the points you're going to be considering are either points where the constraint for some reason is not a C1 function, and therefore you can't use Lagrange multipliers, or in cases where you're looking at some line or segment or curve, the endpoints of the curve. Okay? Doesn't matter which way you do it, either by plugging in the constraint into the function or using Lagrange multipliers. Either way, you have to consider these points. And we're going to see that indeed some of these are going to end up being the minima and maxima. Okay, so now we have a pool of what? We had 1 using Lagrange and then 1, 2, 3, 4, 5, 6. So we have 7 points altogether that we have to consider. Now there's an important statement that has to be said here. So let's clear this board. We found using various methods, we kind of put in the spotlight 7 different points which we claim are potential for being these extremal points. Maybe none of them are. How do we know that indeed our minima and maxima exist and are among these? How do we know that? Answer in German starting with W. Weierstrass, exactly. Weierstrass theorem tells us if you have a continuous function and f is continuous, it's a polynomial in 2 variables, defined on a compact domain, closed and bounded, D is closed and bounded. Do you agree? Okay, it includes the boundary, and it's a bounded domain. Then, by Weierstrass, the function has a minima and a maxima in that domain. Clear? So that is very important, and you're going to see examples where you can find candidates, and it turns out that none of them are minima or maxima. The function could not have even a minima or maxima. You've seen examples like that in Calc 1, right? If you take even, we discussed it. If you take the function y equals x on the open interval 0, 1, it doesn't have a minima or maxima. Do you agree? Is everybody with me? The function y equals x. Nothing sophisticated, no Dirichle, or just y equals x. On the interval 0, 1, no, like this for you, on the interval 0, 1, does it have a minimum or a maximum? On the open interval, it doesn't, right? 0 is not in the interval, so it doesn't have a minimal value and it doesn't have a maximal value. It has an infimum and a supremum, but not a minimum and a maximum. Okay? So same phenomena can happen here, theoretically, but not in this case, thanks to Weierstrass. So you have to mention that. By Weierstrass, since f is continuous on D, which is closed and bounded, and we said the word for that is compact, f has both a minimum and a maximum in D. Okay? So we can conclude that the candidates that we found, these local candidates, the global maximum and the global minimum are among them. So all we need to do now, we don't need to use any second derivative tests of any sort. We can just write the different points that we had. So let's make a chart like this. So this is the point xy, and this is the value of f at xy. And I'm going to list all the various xy's that we found. So we found 0, 0. I'm just collecting all the points that we put in blue boxes before that we had to remember. So we had 0, 0, 1/2 0, 3, 0, 0, 1/2, 0, 3, bless you, 1, 1, and 3 over 2, 3 over 2. Those were all the points that we found, 7 of them, 1, 2, 3, 4, 5, 6, 7. I just felt like Sesame Street for a minute. Do you remember Sesame Street? Do you remember like the song for 7 with the alligator? Said the alligator king to his 7 sons. Ta-da. Okay, never mind. 7. Okay, we have 7 points. How do we find the value of f at each of these points? Right, we just plug in the values. That's not too bad, plugging in very simple numbers like this into a polynomial function, right? And calculate what we get. So it's 0, 0, 0 squared plus 0 squared minus 0 times 0 minus 0 minus 0. It's obviously good, 2. 0, and let me tell you what we get at the other points. You can check. So we get minus 1/4, 6, minus 1/4, 6, minus 1, and minus 3 over 4. That's the values that we get. You can calculate. And conclusion, which is the maxima. Right, these are the maximal values. So the 2 corners of the triangle turn out to be the global maxima of f on this domain D. And what about the minimum? The minimum is this one. the global minimum turns out to be the inner point inside the triangle. Clear? Okay. Remember this statement. This is very crucial in this discussion. We're going to see examples where you get, at the end of the day, you get to a bunch of points, and it turns out that you can't just say the one with the big... It's very easy to just list them, find the one that has the greatest value and the one that has the smallest value and say, hey, that's the max, that's the min. And it could turn out that that's completely not true because it doesn't necessarily have a max and a min. Okay? We'll see examples. Clear? Okay, questions about this? Everybody good? Question? Go ahead. Back to step one on this board. Yeah.
Is that step one? I don't remember what it was anymore. When you found 1, 1, if you had a function that like wasn't a nice little line that was like whatever.
But that's not the function.
The domain.
The domain, okay.
The domain was like whatever. How would you know if the point was inside?
That's a good question. So the question was, suppose your domain was not a nice triangle that you can really comprehend like this, but it was some amoeba. And the equation of the boundary was some gxy equals 0, and you find the point. And how would you verify if the point is really inside the domain or not? In general, there's no recipe. You'd have to figure it out. Okay? So usually you don't just get a picture, you get a bunch of equations which specify what D is. Okay? And then you can check if the point you found satisfies being in D. Okay? So if D is given in terms of some set of equations or some restriction of the form gxy equals 0 or anything of that form, you can verify once you find the point, 1, 1, does it satisfy everything in D? And you can, for example, in this example, even without drawing D, you could check it, right? 1, 1 satisfies 1 plus 1 is less than 3, good. Clear? Okay. More questions? Okay. So what I want to do in the next clip is state and do an example of using Lagrange multipliers for a function of 3 variables. And it's not going to be essentially any different than this, just one more equation. Next clip.